Again, welcome to, we're still dealing with chapter 21 really for where we introduce the concept of charge actually and Coulomb's law. We're going to introduce today the concept of the electric field, which is another way of actually of doing the same things. And also do at least two more problems in here. The key thing with the problems I do is two things. First of all, you're expected to understand them and actually do them on your own. So once you may take notes during the lecture, you may see how they're done and things like that. You have to really go, if they are not part of your homework assignment actually, to actually do them on your own and follow the steps. If there is a step that is not clear or not explained, please let me know that you did this problem, but it seems to me like I probably missed one step or two, or maybe I made a mistake, which is not impossible. As a matter of fact, I do make mistakes, so please catch them, okay? And also, you are accountable for them in the sense that they will really be part of your review for the exam. So the problems we do in lecture and the problems of the homework are your review exams. So if you're asking me down in April, just before the exam, what are the review problems? I just refer to these problems in addition to the homework assignments. Just go do those things. That's going to be your review and preparation for the exam. Is this clear to everybody?
Yes.
Okay. So they're important. They're not just really an exercise they extend the concept and have them basically clarify how to do things with them. But actually, they're also important in the sense that they help you prepare for the actual class. There was a question, actually, not necessarily from, I think it's one of you guys here. It really is an important question. Let me, first of all, get my OneNote in here going. Put this camera down for it. I don't need it. And we are in this section here. And let me go down below. And share screen. Put that out of the way a little. Share screen. Here is the question, okay? And I think it's a very, very good question because you guys really need to understand what's going on. When we did problem 95, I believe, from this chapter, okay? Here is the problem. So we had a charge in here. Oh, why is it red? I didn't mean for it to be red, okay? So we have a charge in here. And we have another charge in here and another charge in here. This, I believe, was Q1, this was Q2, and this was Q3. The problem specifically stated that F3, the force on Q3, due to both Q1 and Q2, was in the negative x direction. But nothing was stated about this line being in positive x direction. This is a right angle triangle. I know it probably doesn't look like it. This distance was 4, this distance was 3, this distance was 5. All of this distances are in centimeters. So we argued that this force in here must be attractive and this force must be repulsive in such a way that their sum is what we called F3 in this case, okay? So we resolved the signs by just looking at the direction of the force F3. And the question was, how do you know that this is actually was in the x-axis? If you try to tilt this problem a little bit and make it actually worse than what it is right now, makes it look like this, okay? So this is still, and then that's by virtue of the problem. It says this is in the negative x direction. Let's say, for example, this is not, clearly is making an angle in here. So this is my Q2 and this is my Q1. This is Q3. Then it's clearly not in the x-axis. As a matter of fact, it's making an angle in here of some sort, theta, for example. This angle was already, because this distance is 4 and this distance is 3 and this distance is 5. That doesn't change. And this is a right angle triangle in here. I could use trig to find what this angle is, and it's very simply equal to the arctan of 3/4. The opposite 3, the adjacent is 4, okay? And this angle is its complement. So whatever this one is 90 degrees minus that. Or if you wish, it's the arctan of 4/3. It doesn't matter. It's the same thing. So if this thing I can't see the chat while I'm in this thing in here, okay? When I'm in the when I'm sharing screens. And I think that's something that Zoom really need to fix. Okay? Anyway, so somebody probably put something in there and I have no idea. So anyway, the point being in here is then the problem really becomes an issue because you really have to solve with it. And I really did solve this problem using with this data. And if I call this one alpha just for the sake of writing this expression, the charge Q2 will be proportional to 1 over the cosine of that sum of theta plus alpha. And the force F3 also is proportional to the same thing. Because remember, the force is due to Q2 and Q1, so it's going to have that factor in it too. It's going to have actually the tangent, which is in part 1 over cosine of alpha plus theta. The reason why I'm saying that is, what happened if I tilt this big time? What happened if I really make this one exactly in the x direction, and this one, it has to be in the y direction because this is a 90-degree angle. So if this is Q1 and this is Q2, then this is the situation I'm looking for. Then Q2 will blow up, will go to infinity because this angle actually right now is going to be 90 degrees. This theta plus this angle is actually has to be a 90-degree angle. And if that's the case, 1 over 0 is infinity. So Q2 will be infinity. And the force F3 will be infinity, will be all the way to the other side. And this force, regardless of which way you point it, this way or that way, it doesn't matter because it's going to be negligible in front of the force from Q2 because Q2 will be huge compared to Q1, okay? And in that situation, basically, then it doesn't matter the sign, and that's how you solve this problem if it's tilted this way. Now, if you tilt it even more, if theta is slightly bigger than that, then you're looking at an opposite direction in here, and the signs will have to be fixed. So we're not in the case 4, whatever that case we were. So we have to change the signs for Q1 and Q2 also accordingly. As a matter of fact, if we keep on tilting the triangle every which way, we're going to get all the different signs, basically possibilities, namely Q1 negative and Q1 positive, Q2 negative and Q2 positive in the combination of all of these 4 of them. So if we keep on changing the triangle. So that's a problem if we really did not, and the problem did not state that Q1 and Q2 are actually in the X direction. The reason why I assumed it was, it's actually from the geometry, from the picture that it was there, okay? And if you take a ruler, you will see that this line for F3 and the line joining both Q1 and Q2 are parallel. So that means that I can assume that it is. Otherwise, I'm dealing with this mess. And this is a very complicated problem. And physics has an advantage over mathematics in the sense that this thing is easier by just a ruler. And some of these problems that we're going to do today will actually or will require the observation. So what I'm trying to say in here is, this is first of all a very good question that the person asked. And you really have to leave a little bit the abstract mathematics a little bit outside and try to think of this problem in terms of real problems. And what is it that meant in the essence in here of this problem? And can I take a ruler and start measuring things? There is a problem, what is it? Problem, I forgot. Okay, we're gonna get into problem 74 today. I have the book in here. I'm trying to get the problem that we're gonna do today. And that's problem 90 actually. So we're gonna do problem, is it problem 90? Did I say problem 90? Yeah, problem 90, okay? Problem 90, where we're going to actually have some data in there and plug in numbers, okay? Which gives you already the way I think, the way I do problems in here. It's not always calculus based, and there will be, okay? It's not always this kind of geometry based, and there will be. But there will be actually data problems, and there will be. Data problems are problem like problem 90. In a sense, this is what we do on a daily basis. We work with data, and we have to interpret data, we have to graph data. That's what we do in the laboratories. So you really need to be at ease with those things. Okay, so that's problem 90. And we're going to actually take the data and work with it. And down the road, you will see more and more problems like this ones where you actually have to bring physics into the problem and you have to actually do measurements, observations, and interpretations and things like that. What you need to do as for this class also to understand it and do it is to have to manipulate data. Working with Excel is going to be big advantage for you guys in this class. So you have to learn how to use Excel in this class. Okay. So I'm glad that the person raised this issue and to share that with you guys. So let's continue. Any questions about this problem or any other problem?
No.
Yeah. Justin, it's not necessarily specified as long as the charges. Actually, there is another situation in here. So Justin mentioned it's actually a good question to think about. If I tilt them so that now Q2 actually will be in the y-axis and Q1 will be in the x-axis. In this situation, it's going to be a problem because I cannot really achieve the case that they want me to achieve because Q1 is known at that point. Okay, and this Q2 is exactly 0. If your Q2 is 0, then it doesn't matter for the sign of Q1 and Q2. There is a lot of issue with this problem if we don't just stick with the things that with the thing. Oh, I'm sorry, I thought about the theta itself. So it's easy to just stick with basically being theta equal to 0. That means that parallel to the x-axis. Okay. So let's continue with this thing in here. We're going to share again the same screen. I'm not going actually out of this screen at all right now for immediately. Okay. So one thing that I did not really talk a lot about it last time is the distribution of charge. Okay. Distribution of charge, when I wrote it down, I believe I wrote it in a discrete fashion. So meaning that using the superposition principle, we can say that the force F on a charge Q. So this is on a charge Q, on Q. Let's make sure that we are specific in here. Is the sum over 1 over 4 pi epsilon naught, we're doing this in vacuum, over all of the charges. Did I write it with Q or I? I think I did I, probably in your class I did I. Hold on. When we got into the superposition principle. This is the same notes from last time, chapter 21. No, we did not even write it. Yeah, here it is. A force on J. Okay, so let's stick with that notation in there, okay? So I have a bunch of charges now. And one of them is J, so it's the sum from I not equal to J all the way to all the charges, okay, included, of Qi times Qj divided by the distance between I and J squared times the unit vector pointing toward J from I. And that's a hat in here, okay? Did I switch the order in here of some sort other than the symbols? It's just the symbols, as long as you know exactly what you're writing in here. Yes, that's correct, RJI, hat, okay? That's really how this is written in this case. This is a discrete distribution, discrete. That means you have 12 charges or 723 or 1,341 or whatever. That's number, okay, like this, okay? So those are the charges we're talking about in here, okay? And you're focused on this charge. This is the jth particle. And this is basically what you're doing in here. You're finding the effects of all of the other charges using the superposition, okay? And adding them up, that is the force on J. Another way of rewriting this expression is actually when the distribution is actually not discrete, but rather continuous. And now you have a charge sitting in here, Q, and it's subject to this distribution of charge. So you have a blob of charges. You have a lot of them, okay? So this is not actually 2D, but rather it's a 3D. So how are we going to handle that? So here is the situation. I'm going to take my object in here and assume that there is some sort of a distribution in here. It does not necessarily have to be uniform, although most of the problems that I'm going to be dealing with will have a uniform distribution. So I have rho in here that depends on where we are in this object in here. So this is r prime is here, okay? So this is the coordinates in some system in here where this vector is r prime, okay? So, and I have a mass in here. So I have an element of charge in here, which is dq equals to rho times the element of volume dv. This is the element of volume dv, okay? So this is 3D. And then, so there is another axis in here that I'm not drawing in here. And then I have to consider this distance in here. This point is somewhere in space of coordinate r. Oops, I cannot draw this vector correctly. So this is r. Obviously, from this geometry, r is equal to the sum of this vector plus the distance between these 2 points. In other words, this distance is just r minus r prime. Okay, I'm just trying to draw the geometry in here. Let me use the other camera if this is my drawing. It's really not easy with this pen on that pen writing thing in here. Let me switch cameras quickly just to draw this thing in here better. And of course, the other one doesn't work well because of the fact that I have to remove the background. So, okay, so let me draw using markers, if I can find the markers. Not the permanent markers though, because it's going to be a disaster if I use the permanent markers. All right, I have the blue in here. What is the, I have the green in here. Okay, I don't have the black one. I don't know what it is. So think of this one as being, first of all, I'm going to choose my coordinate system in here, okay? It's probably upside down for you guys because I'm looking at the screen in here. Probably I should change this. If I put it in front of me, it's going to be a little bit of a problem. So this is my x-axis. This is my y-axis. I'm not drawing the z-axis because it's coming out of the screen, okay? So the z-axis is in here. And I have a blob of material in here. And I have a point in space where there is a charge q in here, okay? So that's basically how this is looking. All I did is I put an element located at a distance in here, r prime, in that blob, inside the volume where the charges are distributed. This is r prime vector, by the way. And this is the position of that charge in space, r, the vector r. Simple geometry will tell me that this vector that links these 2 points is actually r minus r prime. If you're not convinced, just add the 2 vectors, r prime plus r minus r prime, that is r, okay? This vector plus this vector is this vector, okay? Clearly that has to be the case. So then the force now, the element of force from this element only, so dF only, is given by Coulomb's law 1 over 4 pi epsilon naught times the 2 charges. The charge is q, and times rho dv is actually the charge in this case because the distribution is rho. So this is my dq charge. Because I have a rho charge per unit volume, therefore I have rho dv, which is dq per the unit inside the volume dv. So in this case, I have rho dv, that is the actual charges, divided by the distance now squared, which is the distance r prime squared. And this is the magnitude of the force. I have to multiply it by this unit vector r hat in here, okay? And that r hat is the unit vector, I'm going to call it r hat from the point prime, okay? I'm sorry, why did I put this thing in here? Because this changes from the position to position to position, okay? And now my force is going to be just the integral of everything over the volume itself, okay? So I have to sum up over this element of volume. Of course, I have 1 over 4 pi epsilon naught q, which is constants, which has come out of the integral, times rho in this case, which may be dependent. So rho is in general a function of points r prime where we are inside the solid itself, which is a function of r prime divided by r minus r prime. The whole thing squared because we need that distance times r prime. Usually this is a complicated, that's my point in here. This is a complicated integral. Let me switch to the other camera and go back into the OneNote. Are we still on the one node though? Yes?
Yes.
Yeah, I never left it. So hopefully you guys saw the other camera and saw what I mean by this picture, because I cannot draw it well with this thing in there. So the point in here is this integral is very complicated. So the force itself is going to be 1 over 4 pi epsilon naught times the charge q, which I'm assuming it's a point charge, as there is no blob in there, times the integral over volume. And the integral over volume is actually triple integral, which is rho of r prime, which is a vector, dv divided by the distance squared times r hat prime, which is a vector that depends on where I am at in that volume. So this is a complicated stuff, okay? For simple cases, we're going to be able to do this, but for complicated stuff, we have to really pull a computer, C++ or something, and make an approximation or use any computing device to find the actual integral. This integral is not really trivial, honestly, for complicated geometries, okay? So you have to keep that in mind. And again, it's a superposition principle. All I did was take an extension from the sigma, from the sum of the discrete distribution, now to the sum of a continuous distribution. So this is in a case of a continuous distribution with a known distribution with density rho. Which is typically not constant. Typically, it depends on where you are in the volume. If rho is constant, you take it out of the integral, and all you're dealing with is the actual volume of that. Okay. We're going to introduce the concept of the electrical field, and we will see how to find the electrical field. Once we find the electrical field, we find this force. Once we find this force, we go back into F equals to ma. Because I don't want to repeat myself onto this process, because that's exactly how it's going to be all the way to chapter 32, by the way, until the end of the course, I'm going to assume now that the purpose of this whole exercise is to find this force, okay? The purpose of the entire course is to find this force so that we can go back and do F equals to ma or whatever that is, okay? But we're going to discover a lot of phenomena down the road and things like that. By the way, I just remembered, because I'm trying still to get some budget in here, and I'm hoping that the college will clear it for me, is that we will build some motors as part of this course also, once we discover Faraday's law, and you will be building it in your home, okay? So I'm still working on the details of that, okay, and how to do it, at least money-wise, if I can get that going. Okay. So let's introduce the concept of the electric field. You will immediately think that there is something kind of tricky about it. Why in the world do we do the electric field when we can basically work with the force? Okay, it looks like it's a fluke. It looks like it's a mathematical trick, no more. But it's actually a physical concept, and I will explain why that is. So here is the point in here I'm trying to say. Let's take one charge only, single charge. Q prime. Okay, this charge is Q prime, and it's sitting in here, okay, minding its own business. And then I bring next to it a charge Q. Obviously, this problem, we can find the force in here on Q. The force on Q, we have just basically seen how it looks like. It's 1 over 4 pi epsilon. These are point charges. There is no sum or anything like that to worry about. So it's Q times Q prime over the distance squared, where this is the demanded distance, and this is r hat. And we are in business now. All I have to do is compute this value, and I'm done. I can find this force, okay? Instead of bringing one Q charge in there, I'm going to pick up a specific charge. I'm going to pick up Q equals to 1 Coulomb. Okay, so this is called a test charge. You go to the store and tell them I need a test charge that is 1 Coulomb. So you know exactly what Q is. It's exactly 1 Coulomb. So in this case, you find the force exerted on this 1 Coulomb test charge is going to be simply equal to 1 over 4 pi epsilon naught. I'm not going to write 1 in here because I know it's 1 times q prime over r squared times r hat. You attach spring to it if you like, and you measure this force. Spring, and then how much it compresses if the two charges have the same sign. If q prime is positive, it's going to compress for sure. If it's the q prime is negative, it's going to elongate. It's going to put it from the other side, okay? So that's basically the bottom line in here in this case of what's going on. So, let me fix the signs quickly, okay? So if the charge is positive, if q prime is positive, because this is one Coulomb, this is a test charge, it's positive. So that's a test charge. So if q prime is positive, this is a direction for the field. If q prime is negative, it's going to be pulling it towards it. So this is the direction of the force. So this is when q prime is negative. That's it. That fixes the issue of the signs. And I'm not talking about charges that are having signs, having directions. Charges do not have direction. Charges are just values, algebraic values, positive or negative. But the force in this case that results off of this can be pointing away from the charge q prime or towards the charge q prime, depending on its sign. If its sign is positive, it's going to point away from it. If its sign is negative, it's going to point towards it. But this force now is a force per unit Coulomb. By definition, this is what I mean by the electric field. This is exactly what E is by definition. So the electric field is the force exerted on 1 Coulomb charge, that's all. So the electric field is the Coulomb. I'm sorry about the noise, guys. There is somebody in here trying to fix stuff in here, okay? Is the force exerted on a 1 Coulomb charge. Okay? So let's say, for example, you go to the store and you tell them I need a test charge of 1 Coulomb, and they tell you we're fresh out of 1 Coulomb charges. Sorry, can't do. Besides, 1 Coulomb is a big charge, by the way. 1 Coulomb can do a lot of damage. Actually, it can kill people too. So you really don't want to be carrying 1 Coulomb in your hand. That is too dangerous anyway. So they tell you, you know what? We're going to give you a micro Coulomb. Well, actually, they come up bundled in 3 micro Coulombs. That's all. You want that or not? You say, okay, give me that. I'll take it. Okay. You take whatever charge they give you. You attach it to a spring. Obviously, since it's a 3 Coulomb, the force will be a lot less. Okay. So instead of, for example, having to see the spring compress with this much, it's going to barely compress at all so that you notice. And you are still interested in the electric field. What should you do? So you brought another charge. You didn't bring a 1 Coulomb charge. So what you do, you measure the force still, and you divide that force by the charge that you brought into the place, whatever that charge may be, okay? And now that is actually your electric field. Because if it was 3 microcoulombs, which is 3 times 10 to the negative 6, and you measured the force, for example, and it was actually 3 times 3 micronewtons, then the electric field will be just 1 Newton. By the way, the units in this case are clearly, for the electric field, is a Newton per Coulomb. Okay, it's going to be 1 Newton per Coulomb. Had you brought 1 Coulomb as the prescription requires, it's going to compress not with the force is going to be not 3 microcoulombs, rather it's going to be exactly 1 Newton. I'm sorry, 3 micronewtons is going to be exactly 1 Newton. You guys understand? So that is what the definition of the electric field is. So from now on, if I know the electric field, I know what the force is. So the force is simply QE, which is just a rewrite of this expression. Okay. Yeah, so that's basically in a nutshell how this is working. Do you guys have, do you see the point in here? First of all, this is what the definition of the electric field is. The electric field is the force, it's still a force in Newton, exerted on exactly 1 Coulomb though. But if you cannot have 1 Coulomb and you brought any number to the place, positive or negative, it doesn't matter. Just plug it into this expression, see which way the spring goes. If it goes this way, that was actually a positive, the one that you brought. Okay. I'm sorry, it doesn't matter in here. This is the sign that determines the whole thing too. So you preferably a positive. If it's negative, you just take its absolute value. And so since you're looking at the magnitude is going to be just the magnitude of force over charge. Now, the direction of this force also is the 2 charges in here. If this was negative, the one that you brought, okay, and this was actually negative, so in this case, the force clearly has to be repulsive. And this was positive, clearly the force has to be attractive, and the negative will come in here in this way, okay? Ignoring this Q in here with its sign and its value, the electric field by itself has a meaning in this case. So it's really not a mathematical fluke, because it looks like all what we did in here is just juggle this expression, that's all, and move Q from here, and it define a new quantity that does not have Q in it, this being E, and then if you bring another quantity other than 1, you just multiply by that, and now the problem solved. If you're curious trying to find the electric field of 2 charges, you use superposition principle. 3 charges, you use superposition principle. In other words, the superposition of 2 charges will give you the electric field of 2 or more charges, and so on and so on, okay? And you can use actually the integral too. With the exception now, I don't have to deal with that Q inside the integral, that's all. What is the definition that I have in here, okay? This Q will not appear there, and that's the end of it. So the electric field will be without that, because that's 1 actually for the electric field, and now I have to deal with this very complicated triple integral still for the electric field. In other words, I shifted the difficulty from one quantity that has to do with the interaction of 2 particles in the presence of a third one that I'm trying to find forces on it, to just basically the charge itself trying to do things. Let me explain what's going on in here. I'm going to take my charge in here. Let me erase this stuff in here before it dries, because it's very hard to erase this. Just remember that. Let me take a charge now, Q. Charge sitting by itself, minding its own business. For the sake of argument, I'm going to take it positive. Remember, all that happens if it's negative, everything else will be just opposite, that's all. And I bring 1 Coulomb, and put it at some distance. It doesn't matter where. Here, for example. Now, this is 1 Coulomb, okay? Attached to a spring, and see which way the spring compresses, because I assume this one positive, so it's going to compress if it was attached to this side. And the force I'm going to measure is here. Actually, what I'm measuring is E now, because I brought 1 Coulomb in there. If I move it closer here, the same 1 Coulomb, it's going to be this much force, okay? If I move it further, it's going to be this much force. So that is the electric field the way I'm envisioning it right now, okay? If I move it around in a sphere, let's say, for example, that's not a circle, by the way. I cannot draw a circle on a flat screen, so I'm drawing a circle instead. So this is a sphere. If you move around on the sphere, it's going to be the same force, with the exception that the direction changes, that's all. Because this electric field will be radial, pointing away as if it's a hedgehog moving in every direction in this case. Okay, with the same value, because remember, its value, because this is a point charge, is always 1 over 4 pi epsilon naught times Q, this Q, divided by the distance squared. And since I'm on this sphere now of radius r, then the magnitude of this vector does not change. The only thing that changes is actually is r hat, because this is radial. Okay, since I'm changing location, then the direction changes, that's all. But the magnitude of the electric field on the same sphere is the same. It does not change. It's the same value. If I move closer, it increases like 1 over distance squared. If I move further away, it drops for the same reasons as 1 over distance squared. So that's basically how the image is. Now, take my test charge and drop it out. put it away. We don't need it anymore. So what I say in this case is the electric field actually changes the surrounding of a charge, Q, in such a way, if I bring now another charge, it's not the 1 Coulomb, any other charge you want to, that charge now is going to be subject to a force equal to, let's say, for example, now I bring another charge now in here. I'm going to call it Q prime. This charge actually, and I know the electric field in here. I already calculated it in here. This is E. So I know the force is going to be Q prime E. So that is the actual force. So a charge has to be fixed, though, okay, will change its surrounding in such a way that by creating this electric field around it. So a charge changes its surrounding by creating an E field. The E stands for the electric field. So now, do you guys understand what this is? So this is a physical thing, and I can measure it with this test charge. I can actually do it. And there is a lab for that too, okay? There is a lab for that too. I'm not sure if we can do a simulator or not, but what we do actually in the lab, we have this conducting paper, and we put pins on them, okay? And those pins are conducting materials, and we attach them to a battery. Actually, one of them from one side has a lower voltage, and the other one has a higher voltage. And since this is a conducting, an electric field is created actually between the region, and we take a voltmeter actually, and we measure the regions where the voltage actually is changing. And we will see that there is a relationship in 2 chapters from now between the voltage and the electric field. And you will draw the electric field. The field lines, actually, these are called the field lines that you're going to be drawing for this geometry. In this case, you're going to draw the field lines emanating from the positive charge. If this was a negative charge, the field lines will be completely the opposite. That's all. So this will be pointing in, this will be pointing in, this will be pointing everywhere. It's the opposite of a hedgehog. This basically is collapsing on itself, basically. All of these field lines will be pointing towards this one. And the closer you are, the stronger they are, and that's it. So that's basically how this looks like. So that is the electric field as we define it. Now you ask, what is the electric field of 2 charges? Well, it's by superposition. That's it. Just add the electric field of the 2 charges. Any questions so far before I jump into example 96 first? Not the example, no. That is problem 96.
None at all. I'm pretty good.
Okay, so let me get into problem 96, and I'm not going to actually do problem 96 because we did problem 95 and it is similar. Okay, problem 96, which you're accountable for it too, by the way. You have a charge Q1 in here. This is identical to the first problem. And you have Q3 in here, Q2, I'm sorry, in here. And this was actually a distance of 5 centimeters also. And I'm not drawing to scale, so I'm just drawing things in here. This distance was 3 centimeters, and this distance was 4 centimeters. And the problem tells you, in this point, there is no charge in here. There is no such a thing as Q3 in here. There is no charge in here whatsoever. Just a point in space, P. Okay? The electric field E is pointing this way. Okay? And they give you the Q1 being a given value, 2 microcoulombs, I believe. We don't know its sign, but we don't know the value and the sign for Q2 either. And they give you Q1 being a specific number, I think 2 microcoulombs, and they want to know the direction and the magnitude of the signs for all of the 3 charges. First of all, for all of the other 2 charges. For both charges, I'm sorry, there are no 3 charges anymore. And then they want to know the value of E, the electric field in this case, given this geometry, okay? So let's think about this problem. First of all, because of the direction of this electric field pointing in this direction, this must be a negative charge in order for me to produce this sum of these two vectors. And this 2 must be a negative charge. So I already resolved the issue of the signs. So if they gave me a value in here, it's negative 2 microcoulombs. And this one, I still don't know its value, but it's negative nonetheless. Okay. So that fixes the issue of the 4 different possibilities. This is the only sketch that's going to work for us in here. Okay. That's one thing. The other thing for this problem is, I know the magnitude of this vector. The magnitude of this vector is exactly 1 over 4 pi epsilon naught times q over this distance squared. Don't forget to convert it into meters though. Okay. And this is a microcoulomb, something, 2 microcoulombs or something. And once you do this expression, you have to take it in absolute value, because I already took care of the sign by doing the vectors in here. Okay, so do not do double jeopardy in the sense that you already have a sign direction and then you append the sign, and this force will point in the opposite direction all of a sudden. Okay, not force, this is electric field. So this is E1. The same thing now, I need to do E2. E2, I don't know what this Q2 is, but I know the force, the electric field must be equal to Q2 again, in absolute value, divided by that distance squared converted to property. Okay, so that is the 2 electric fields in here. They tell you that it points in the y direction, so that means the y component of this one and the y component of the other, they must cancel. And the y component for this one, I mean the x component, I'm sorry, the x component is this one for this vector, and it's the adjacent to this angle, which is this angle. So it's this magnitude times the cosine of this angle, which is the cosine of that angle, which is 3 over 5. So I multiply 3 over 5 times E2 and must equate it to, again, this angle now and this angle are the same, and it's the cosine of this angle, which is this angle, because it's adjacent to this angle too. And that is 4 over 5 times E1. So these two must be equal to cancel one another so that there is no x component. In the y component, so from here, I will have a conditional Q1 and Q2. Because I know Q1, I don't know Q2. From here, I can solve and find what this equation is. Now, if I want to find what E is equal to the sum, again, by superposition of E1 plus E2. Okay? And since it is equal to the sum, in this case, it's going to be the x, this component of this one, which is the opposite to this angle, which is the sine of that one. So it's going to be basically E2 times the sine of this angle, which is simply the opposite over the adjacent, 4 over 5, plus, because both of them are in the same direction and they're negative actually, plus, again, this vector E times the sine of this angle, because that's the opposite again. So it's the sine of that angle, which is 3 over 4. So it's, again, it's going to be E1 times 3 over 4. And that's going to give me my E pointing properly in the negative direction. So that's problem 96. Okay. So you guys can finish it. That's one of the tasks that you're going to be doing in here, is to actually finish this problem. This is item 1 of the discussion. Is this clear for problem 96? Can you guys finish it?
Yes.
If you guys have difficulty with it, please let me know. Do not struggle on your own and spend more time on it than what you need, okay? If you think that something is not clear or you're not getting the right answer, please let me know so that we can move along with it, okay? And that is the key thing in here, is the electric field. Please understand there are no forces anymore. It's just electric field. There is nothing in point P in here. There is absolutely nothing in that point, okay? Okay. How much time we still have? We still have quite a bit of time. So before I jump into problem 90, what is it, 90? Let me talk about 2 things, okay, that we will need before we do that. And one of them is the dipole, electrical dipole. Okay, this is a big deal, by the way, the electrical dipole. Electrical dipoles are everywhere, okay? Your antenna is a dipole. That's why they're called dipolar antennas. And molecular structures, they're all, a lot of them, not all of them, have dipolar structures, like the water molecule, for example, it's actually a dipole. And that's actually accounts for the van der Waals force between the water molecules and causes a surface tension actually on the water itself. And actually it's responsible for so many things, okay? So again, because basically the charges, yes, the electrons, they are shared between the proton, the hydrogen atom and the oxygen atom and the H2O molecule, but the actual electron move closer to the oxygen atom than they stay near their hydrogen atoms. And in a sense, that displacement will create a situation where you have a charge, a net negative charge closer to the oxygen atoms, then and leave behind them a net positive charge basically near where the hydrogen atoms are. And you will have a situation that look like this. Basically, you have a negative charge Q in here and a positive charge Q in here, okay? So that is the cases in it. The distance between them, that is by definition 2A. In other words, this is an A and this is an A, and half between them is where usually the position, the center of symmetry, if you wish, between these two charges. Q is the same. So a dipole basically is made up of two charges separated by the distance 2A, not A, 2A, okay? And you will see the advantage of using 2A rather than just a distance A or distance D or something between them. Here is a question. What is the electric field here? On the same axis between them at a distance x from the positive charge. So this is the origin of the axis, and this distance is x. Obviously, the distance between the positive and the point where we want to, that is actually x minus a. And the distance between the positive charge, the negative charge, and where we want the electric field is actually x plus a. Do you guys see that? Because this point in space P is located at the distance x from the origin. And I need to know how far it is from both charges, the negative and the positive, in order for me to find the electric field there. Yes? You guys see the geometry? I need a confirmation. Yes. Okay, so in this case, the electric field due to the positive charge is simply equal to, and it's going to be pointing this way. The electric field from the positive charge is going to be pointing away. The reason is because this is positive. So the electric field from positive charge always points away from it. If I'm interested in the electric field from the negative charge, is actually pointing toward the negative charge. And it's a lot less because this distance x plus a is more than x minus a. Remember, it's proportional to 1 over the distance squared for the single charge. Okay? So here is the deal. I want to find E plus first. E plus is equal to 1 over 4 pi epsilon naught times Q divided by the distance squared. And the distance squared is clearly equal to x minus a squared. Okay? The charge, the negative charge is already taken care of in terms of the sign in here for the electric field for E minus. I should not write it as a minus anymore when I write E minus, okay? I already took care of the business of the signs by drawing the graphs in there. So it's going to be 1 over 4 pi epsilon naught times Q in absolute value, because Q is the same for both of them. One of them is negative, the other one is positive. So divided by the distance squared, which is x plus a squared. So that is the electric field. Now comes the superposition principle, your BFF. So in this case, E is equal to E plus minus E minus. The reason why I'm doing a minus is clearly because, first of all, I didn't account for the minus already. I accounted for it in geometry. So the sum of these two algebraic quantities is one of them is positive, the other one is negative, so it's going to be the difference of the two. Okay, so all I'm doing in here, since the 1 over 4 pi epsilon naught and Q are common factors, I'm going to take them out. So this E is going to be Q over 4 pi epsilon naught times the E plus. The E plus has a minus in it, x minus a squared, minus the E plus, the E minus, which has a plus in it, x plus a in it squared. The common denominator of this expression is x minus a squared times x plus a squared. I'm going to write it as x minus a times x plus a squared. Square the whole thing. So the denominator first. Okay, since you don't want to write the whole thing. Denominator is going to be the product of x minus a squared times x plus a squared. I'm going to write this expression as x minus a times x plus a, the whole thing squared. And there is an identity that you guys saw way back when you were doing this stuff, when you were a lot younger than now, is x minus a times x plus a. Do you guys remember what that expression looks like?
Do you mean difference of squares?
Yes. No. Yeah. So it's x squared minus a squared. Do you guys agree?
Right.
Yes.
Yeah.
So this is x squared minus a squared. Don't forget that the whole thing is squared. So that is my denominator. My numerator, though, it's going to be x plus a squared minus x minus a squared. The numerator, though, is going to be x plus a squared minus x minus a squared. Okay, again, that is equal to, excuse me, I have a square minus square. Can I factor this thing out? It's the same thing, except backward. Yes? You guys agree? This is like the first expression, except
Yes.
what happened to the pen now? Oh, no. Okay, good. Do you guys see that this is x plus a plus x minus a times x plus a minus x minus minus a, which is plus a. Does this make sense? Is it the same thing or not? If you're not convinced, you just expand the thing, okay? Yes?
Yes.
Yeah, it's the same thing. If somebody is not really happy with this experiment, all you have to do is expand this one. This is going to be x squared plus a squared plus 2ax. And this is going to be x squared plus a squared minus 2ax. But don't forget you have a minus in front of them. So the x squared cancels the x squared, the a squared cancels the x squared, and 2ax plus 2ax is going to be 4ax. So the bottom line is this a and that a will cancel, and this x and that x will cancel, and it will have 2x in here and 2 a's in there, so it's going to be 4ax. Okay, one way or the other, the numerator is 4ax, and the denominator is x squared minus a squared. So I found the electric field in that point, and the electric field is going to be E is going to be Q over 4 pi epsilon naught times 4ax divided by x squared minus a squared squared. Here is what I'm going to make a simplification between the 4 and the 4 and divide this by 2. I'm left with a 2, and divide this by 2 and left with 2. And you're wondering why in the world you didn't cancel the 4? No, because 2a is a real thing. It's part of the distance between the negative charge and the positive charge. So I don't want to get rid of that distance. So I want the whole distance. I don't want half the distance, okay? And I'm going to define, so this expression will be 2a times q. And 2a times q by definition is going to be p. So p by definition is equal to q times 2a. And this is what I mean by the dipole moment. As a matter of fact, the dipole moment is a vector that is equal to the charge times the distance between the negative charge and the positive charge, emanating from the negative charge to the positive charge, and that is in this case in the I hat direction. It's pointing from the negative direction, from the negative charge to the positive charge. So this vector could be this one in here. So this is probably what we're talking about. So this is P in this case. So it's a vector that is pointing from the negative charge to the positive charge, whose magnitude is equal to the charge times the distance between the negative charge and the positive charge. So written in this way, and since P and E are clearly parallel to one another, since E is all of it in the x direction, so I can write E now as simply equal to, remember, I have a P now times X, so it's going to be PX or XP. So E as a vector is X times P divided by 2 pi epsilon naught times the distance squared, x squared minus a squared squared. Okay. A particular case of interest is far away from the dipole. This is called the dipole approximation. The dipole approximation means when x is very, very large compared to a, which means that x squared is very, very big compared to a squared, which means that x squared minus a squared is roughly equal to x squared, because a squared is negligible. That means I'm looking to x squared in the denominator, and e will be, I'm just taking its magnitude, will be the x cubed, x squared and x to the power 4 will cancel and will be left with just one of them. So it's going to be p over 2 pi epsilon naught times x cubed. So the electric field drops as the cube of the distance, not the square of the distance in the case of the dipole, because one of the charges is shielding the other. So it's weakening the effect of the electric field in this case. Here is another case of interest in the case of the dipole. So what we calculated in here is the electric field on the axis joining the two charges. If I want to find the electric field on a point other than the axis in here, it's going to be complicated. So I'm going to change the axis in here. And this is the origin O still. This distance is A, this distance is A, so that the negative charge and the positive charge are always situated at the distance to A. But this is a point Y, and I want to find the electric field now there. So what I do in a similar fashion, I find the electric field due to this charge and the electric field due to that charge. This one is going to be pointing away because it's positive. This is going to be pointing toward because it's negative. The magnitude of the E plus and the magnitude of the E minus, both of them are going to be this distance squared, which is this distance squared. This is Y, by the way. So this distance is going to be the square root of, by the Pythagorean theorem, as a squared plus y squared. So the distance is the same. So the magnitude only will be equal to Q over 4 pi epsilon naught times the distance squared, which is y squared plus a squared. Okay? So this is the magnitude of the electric field now in this case. However, in this situation, it's clear that the y component, by the way, this angle and this angle are the same because the cosine of this angle is equal to y over this hypotenuse. And the cosine of that angle is y over the hypotenuse, the same hypotenuse. They have the same cosines, they have the same sines, they have the same tangents, as a matter of fact. This is tangent of, you see, a over y, the arctangent of a over y, and this is also the arctangent of a over y. Therefore, these two angles are identical, which means that if I'm looking at this vector in here, its components in the y direction, this is its components. The components of this vector into the y direction, it's actually this component, and I'm dealing with the same cosine of this angle, which is the cosine of that angle, and that gives me 0. So in other words, this distance and this distance are the same, and this vector has no y component. But if I'm looking at its x component, the x component actually is going to be in the negative y direction, in the negative x direction, I'm sorry, and it's going to be simply the cosine, the sine of this angle times one of them, because the sine of this angle times the other one is the same. So I'm going to have twice two the same values. I'm going to have double the sine because they're same magnitude. So when I project them in the y direction, so I'm going to look at the x components of the electric field, which is the total field, by the way, and it's a negative value. It's pointing in the negative direction, so I'm going to restore the negative shortly. But I'm going to say it's E is equal to 2 times E plus or E minus. They're the same value, okay? So it doesn't matter which one I write in here, times the sine of that angle. And the sine of the angle is the opposite over the adjacent, the opposite over the hypotenuse. It's A over that square root that I was talking about, y squared plus a squared, the hypotenuse. So plugging these numbers in here will give me E. I wrote E plus, you could write E minus, it's the same magnitude. So E is going to be equal to 2 times 1 over 4 pi epsilon naught times Q over, remember, it had an y squared plus a squared, that's the electric field, times now the sine, and the sine of that angle is a over the same quantity, except that it's lifted to the power 1/2 instead. Obviously, 1 plus 1/2 is 3 halves, I'm sorry. And the answer is going to be the 2, instead of canceling it with the 4, I'm going to multiply it with the a in here and redefine my q times 2a again, which is p. So e as a vector now, it's clearly pointing in the negative p direction, p over 4 pi epsilon naught times y squared plus a squared to the power 3/2. Okay, so if you're wondering what happened to the a and the 2 and the q, they all became p now as a vector. P, remember, is pointing in the I hat direction by definition. So it's related to the dipole moment still. Okay. Again, go to the dipole approximation far away from the dipole, namely that y is much, much bigger than a. That means that y squared is much, much bigger than a squared. That means that y squared plus a squared is roughly equal to y squared. And if I raise this one to the power 3/2, so this one is going to be to the power 3/2, is going to be roughly equal to y squared to the power 3/2, which is just y cubed. So the denominator also will have a y cubed in it. So the electric field in this situation is going to be equal to minus p. This is very far away from the dipole, not near it, y cubed. Near it, you have to use this expression. If you are on the y-axis. If you are in the x-axis, you have to use the other expression. This expression, if you are on the x-axis, okay? So, but that's the only two conditions that we can do up to this point. Later on, when we learn about the electrical potential, we should be able to calculate the electric field anywhere we wish, which is kind of powerful stuff, okay? But at this point, we're limited only to these two axes where we can do the actual calculation. A point of interest in here, in this situation, far away from the dipole, it's 1 over 4 pi epsilon naught, the distance cubed. And on the axis itself, it's 1 over 2 pi epsilon naught times x cubed. So if I am looking at a dipole, and if I check it around, I will see that if I am on the axis, the electric field is twice as strong if I am on the other side in there. So I know I'm dealing with a dipole in this situation, okay? So that is basically the dipolar intersection and how this problem is situated. Okay, any questions about the dipole before I jump into the example from?
No.
Okay. I trust that you guys are doing, because they're going to be quizzed on these things and tested. So hopefully you guys are following the materials. If you have questions, please do not hesitate to ask, because the last thing I would want to see is that you guys struggling with these concepts. Okay. So problem 90. Let me switch cameras again, because it's probably easier to do it on this. So let me remove this thing in there. What happened to my black marker? I like this one in here. Like the black marker. Oh, here it is. Found it. No, that's actually a red one. That means the black one is not too far from it, and it is here. Sure enough, I got all my markers. Okay, let me switch cameras. And it's actually this camera, except that again, I have to fix that thing there with the background. Okay, so we have this camera in here, and probably it's kind of dark a little. I didn't know that it was going to be this dark. Hopefully it's not that dark anymore. Okay, so problem 90. That's the problem we're going to be doing in here. So I'm hoping that you guys will follow this discussion. And that's on page 715 from the 15th edition. So it says a positive charge Q is distributed uniformly along the a ring of radius A. So let's do the ring first of all, okay? We need to find the electric field of the ring, and you measure the electric field at a points on the ring axis at a distance x from the center of the ring over a wide range of values of x. So let's do that. Let's take a ring first of all and find the expression for it, because we will need that expression. So here is a ring, okay? And I am at a distance x from it, and I want to find the electric field from it. So what I'm going to do is the following. I'm going to take an element of the ring of length ds. And I'm going to assume that the charge is distributed uniformly, as it specifically states that Q is distributed uniformly. That means if I take Q and divide it by the entire ring, which is 2 pi times the diameter A, the radius A, this radius is A, that is going to be a uniform distribution, which I'm going to assume it's lambda. So what lambda is measuring in here is how many charges, how many coulombs per unit, per meter, basically, on the ring itself. So if I take an element, ds, I have lambda times ds. That is how much charge I have in that element in there. Lambda is constant, by the way, because it's uniform distribution. So lambda is not changing, okay? So I want to find the electric field that this element creates, because, again, the law that we have found actually is just for a point charge. So I'm going to assume that dq is actually a point charge. So this is the distance in here that I am considering. And this is the electric field created by that element, dE. So dE is equal to the 1 over 4 pi epsilon naught times the charge. And the charge is lambda times ds divided by the distance squared. From this is the distance x, by the way. And this is A. So this distance squared is just, by the Pythagorean theorem, is a squared plus x squared. That is actually under the square root, but I'm going to square it anyway. So it's going to be x squared plus a squared. Okay, but that's the magnitude of E. That is not the entire story, though, because if I go to the other side now of the element, this one, for example, let me pick up another color. Anywhere, because we're going to go through the entire ring. So one particular point of interest is this one, for example, the same size. So it's going to have an electric field in this direction. Obviously, this component of the electric field and this component of the electric field, they cancel, okay, because they're same magnitude. Both of them have that denominator, so x squared plus y a squared. Both of them are lambda ds. Both of them have 1 over 4 pi epsilon naught. One of them is pointing up, one of them is pointing down, so their y component cancel. So the only component of interest really is the one in the x direction. So the only component that is going to matter is this component when we sum. So we're going to take only the one of them and sum through the entire circle, through the entire ring. In doing so, basically, we're only going to pick up the contribution from the x-axis in this direction. Obviously, the contribution of the x-axis, I have to multiply. This is the adjacent to E. So I have to multiply by cosine of this angle. And the cosine of that angle is actually the cosine of this angle, which is clearly x over that hypotenuse. So in other words, I have to really sum up. So this is magnitude only. So this is mag, the first one that I did. So now the actual vector itself in the x direction, okay, is going to be 1 over 4 pi epsilon naught times lambda ds over x squared plus a squared times the cosine of that angle, which is clearly x over the hypotenuse, x over the same square root of x squared plus a squared, okay? And when I sum through this, ds changes from 0 to 2 pi a, okay? And nothing changes in here. X is fixed. This point in space is fixed. A is fixed. The ring radius is fixed. And epsilon naught is fixed. Lambda is constant because it's uniform distribution. So everything else comes out of the integral, and E itself will be simply equal 2 pi a times everything else. So it's going to be 1 over 4 pi epsilon naught times 2 pi a times lambda, and 2 pi a times lambda is nothing but q, okay, times x divided by x squared plus a squared to the power 3 halves. So that's the result that we're going to end up with. So I'm going to just sub the value of Q in here, in there, and I'm going to use that as my expression for the electric field on the axis of symmetry, a distance x from the center of the ring, for a ring that has a charge Q on it and of radius R, radius A, I'm sorry. So it's going to be basically equal, the electric field then is going to be equal to 1 over 4 pi epsilon naught times Q, because remember that quantity 2 pi A lambda is Q, times X divided by X squared plus A squared, the whole thing to the power 3/2. So that's the result I'm going to need for this problem. Okay. The derivation actually is in lecture, okay? So if you, it's in the book. So you guys, you can go to the book and look at it. We still have about 15 minutes, so I'm hoping to quickly finish these questions in here. So you measure the electric field at points on the ring axis at a distance x from the ring center over a wide range of values. Your results for the electric field for the larger values of x are plotted. So when x is very large, they gave you the plot, okay? And they tell you as EX squared. So what we're gonna plot in here, not E, but E times X squared, which is according to this math should be 1 over 4 pi epsilon naught times Q times X cubed, because we multiply by X squared in this expression to plot it, divided by X squared plus A squared to the power 3/2. Okay. So that is basically what they have plotted. They didn't plot E, they plotted EX squared, and they gave you the plot. Okay. Explain why the quantity EX squared approaches a constant value at increasing as X is increasing. So when X increases, when X goes to infinity, if you like, when X over A, to be more specific, goes to infinity, X becomes much larger. So A is going to be neglected in this expression. So I'm dealing with X squared to the power 3/2 in the denominator, which is X cubed. And I already have an X cubed in the numerator. So the X cubed cancel the X cubed, and the limit of EX squared will simply be equal to Q over 4 pi epsilon naught, because the numerator has an X cubed in it. It's super large, it's blowing up. And the denominator will be dominated by X squared in this case, over A squared. So it'll be X squared to the power 3/2, which is exactly X cubed too. So the X cubed and the X cubed will cancel, and the limit will be constant. It's going to be exactly this number, Q over 4 pi epsilon naught. So whatever charge was in the ring divided by 4 pi epsilon naught will give me that value, okay? Okay, use the figure to calculate the net charge Q on the ring. If you look at the figure, you will find that this limit is Q, is 45, I'm sorry, in their SI units, which is a Newton meter squared per Coulomb. So if you solve this expression in here, you're going to find Q to being equal to 4 pi epsilon naught times 45. And this number is 1 over 9 times 10 to the power 9. I mean, this number, 4 pi epsilon naught times 45. So it's going to be 45 divided by 9 times 10 to the power 9. 45 divided by 9 is 5. 10 to the power 9, when you take it upstairs, is going to be a nanocoulomb. So Q is going to be 45 over 9, which is 5 nanocoulomb. And that's the answer to the question. Okay, so that's question B. We're doing on time. We still have time. Okay, question B. Question B. Your results for smaller values of X are plotted as E over X. So now for smaller values of X, they didn't plot EX squared, but they are plotted instead E over X. So they plotted E over X for small values of X. And E over X, if you look at it, you get rid of that X, is going to be 1 over 4 pi epsilon naught times Q, which we know it's 5 nanocoulombs, by the way. So I know the ratio of Q over 4 pi epsilon is exactly 45. So this ratio is exactly that number that we were talking about. Divided by X squared plus A squared to the power 3/2. Okay, so that's basically what that expression looked like, because they said that they plotted E over X. They didn't plot E. Okay. Explain why E over X approaches a constant as X approaches 0. So if X goes to 0, this goes to 0. So I'm left with an a squared in here to the power 3/2, which is a cubed. So E over X will approach, of course, 1 over 4 pi epsilon naught times Q over a squared cubed. That means to the 3/2, I'm sorry. So that means a cubed. And this is constant, doesn't depend on X. So it's going to approach a constant, okay? And use the graph to find A. So from this expression, we know from the graph, if you look at the graph, this is 700. This constant is exactly 700 in SI units. Q over 4 pi epsilon naught, that's actually 45. So 45 over A cubed is exactly 700. And from here, I'm going to find EA equals to, what is it? The cubic root of 45 over 700. Cubic root, not the square root, okay? Here is your task. You need to finish the algebra and check the my calculations, okay, to make sure that I didn't do any mistakes in this problem, okay? Any question about this problem? I hope that you guys redo this problem again because you're accountable for these things again. Does this thing make sense to you guys?
I think for now, yes.
Yes.
Okay, very good. Let me go to problem 74 because that was a problem that I gave in an exam in the past, okay? So that's going to be the last exam from this last example from this chapter. And then next time when we meet, we're going to be actually doing chapter 22, which is Gauss's law, which is another way of actually finding the electric field. Problem 74. So basically, they gave you a charge Q of 72 nanocoulombs, and they are the same charge, okay? And they gave you the mass of these particles, and they told you basically it's hanging from a ceiling. So we have a ceiling in here. So this is a charge Q, and this is another charge Q. One of them is 72 nanocoulombs, and the other one also is 72 nanocoulombs, and they're hanging from a ceiling in here of some sort. They gave you this angle. So we need actually half of that angle. This angle is 58 degrees. So theta is equal to 58 degrees. And we need half of that because we need theta over 2 for the calculation. And what they want to know is, they applied the electric field, as a matter of fact, to the whole thing, okay? When they are tied to the ceiling hook by a light string. So they gave you L. You need to know L, this too. They gave you 53 centimeters long of the string length, okay? So you know this distance now. You know how far the two charges are separated. Because if L, you know it, and you know the angle, then you can use just simple geometry to find this distance, which is half of that, which is the opposite of this angle, opposite of theta over 2, or 29 degrees. And then you do the algebra in here, okay? But now, when a horizontal uniform electric field that is directed as in to the left on the spheres, they hang at that. So the only reason, because one of them is positive, the other one is negative, is that because you applied actually an electric field. If you apply an electric field in this direction, E, the positive will move this way because it's going to be subject to QE to it. And the negative will move this way because it's going to be subject to negative QE. Because you applied it this way, the negative charge will be negative charge times E, and the positive charge will be the positive charge times E. Obviously, this is positive, and this is negative. If they moved in the opposite direction, then you're fine, okay? The electric field is, the charges will flip, okay? So if the electric field was applied in the opposite direction, the negative will move this way, and the positive will still move this way. So this still positive, and this still negative if you apply the electric field in the opposite direction. Sorry, what did I say? I said nonsense. I'm sorry. I'm sorry. So if you apply the electric field this way, the positive will move this way and the negative will move this way. So they actually will crisscross each other. So they will be moving in the, so don't do that, okay? If you're going to do it, you have to be careful how you apply this electric field, okay? If you see yourself, you're messing up, you're entangling this thing in here, that means you have to reverse the polarity of the electric field. Okay. But that's the positive and that's the negative. The correct answer is that way. So which ball, the one on the right or the one on the left, has positive charge? Of course, we answered that question now. What is the magnitude of E? Now we need to find the magnitude of E. Something you did way back when you were doing physics for A, namely the free body diagram. they gave you masses. So I'm going to focus on only on one of them. So I have mg in here. I have the tension also. I have another color. So I have the tension here, T. And I also have another force. And that force is actually this attraction between the two of them. This force is equal to Q times Q, both charges, Q squared basically, 1 over 4 pi epsilon naught, times the distance squared, this distance squared. So twice this much squared, so the distance squared. And that you need that too in your calculation. It may be negligible, but you need that in your calculation. So you have 4 forces. You project in the x direction, you project in the y direction, and everything should cancel. The trouble with the projection in the x direction, you have QE is canceling part of this force, but there is a tension also that has a component in here. So you have to take the tension component in here, and you don't know the tension, but you can find the tension from this y component as it cancels the mg in here because the whole thing is in equilibrium. This was a part of a problem that I gave in the exam. It doesn't mean that I'm not going to give it in this exam. It doesn't mean that I'm going to give it in this exam, but you guys need to know how to do these problems and understand them. Okay, let's change camera too. 3 questions?
No.
Okay, you guys don't
I have
have
a
any
question.
Yes.
So did we know that the one on the left was the one with the positive charge then? Because the electric
Which way
field
the
was
electric
moving to
field
the
was
left.
pointing and the charge moved with it. That is the positive charge.
Okay.
The
So I
one that
guess the
moved
electric
in the
field
opposite
repelled
direction
it or
was
something.
negative. Sorry?
Did the electric field repel the positive charge since it was also positive?
The positive charge will move in the direction of the electric field.
Okay.
Okay. Because Q times E, that's the key thing in here. The electric field, the force is Q times E. So if we see a charge moving in the same direction, that means that that charge is positive. The charge that moved in the opposite direction, that was actually the negative charge. Okay. It doesn't help that the electric field is negative. That is actually irrelevant. The electric field is pointing in the negative direction, so what? Then the force actually in the negative direction too, because Q is positive.
Okay.
Hopefully that lifts any confusion in there. Okay. So you guys have your items. I will see you guys on, do we have the discussion for part 2 for this chapter 21? I think I have, but let me fix it quickly in here because it needs some fixing in here. Oh man, let me edit this. Okay, the discussion will be open very shortly, okay, for this chapter. And I will see you guys Thursday. We have lab on Thursday, don't we? We're gonna meet on Thursday. Okay, I'm gonna stop the recording first quickly here.